Hello and welcome to this podcast on work, energy and power. That's the name of a sort of subtopic, and we'll be specifically looking at work and energy. So, doing work. Work, obviously, in English is a word which just means, any kind of activity, really. But in physics, it has a very specific application. It means converting energy from one form to another. In particular, a type of work called mechanical work relates to the sort of situation you see in this diagram where you're applying a force over a certain distance. And the equation is quite simple. The amount of work that is done equals the force multiplied by the distance moved in the direction of the force. So the unit of that, well, the unit of force is the Newton and the unit of distance is the meter, so it's the Newton meter, but we give that a special name. We call it the joule. So 1 Newton meter is 1 joule. So work done equals force. The force applied in the direction of movement, so that's F cos theta, where theta in this diagram shows the difference between the direction of movement and the application of a force, and delta x is the change in position, as shown in the diagram there. So, quick question, is this woman doing work? Well, obviously she's doing some sort of work, but she's not actually moving. The work she's done, the heavy load that she's carrying is acting up and down, and her movement is horizontal. So the equation might seem to say no. But if you're talking about people doing work, it's a bit of a different situation because people use their muscles. And when your muscles are contracting in order to carry heavy loads. So our muscles are always doing work whenever they're actually doing anything in any direction. So that's a bit of a different case. The other thing to point out is that work done is a scalar quantity. Now, force is a vector and distance is a vector. So you might say, hey, vector times vector, but actually it's just the magnitude of the force that we're interested in. So you could write this using that symbology where the two lines indicate that the thing inside is just a magnitude, but we won't bother. The data booklet, by the way, writes this as work done equals Fs cos theta, where the S stands for displacement. We can draw a graph of this, similar to how we've done this drawing graphs previously. You could draw a graph of the application of force and the distance over which it is moved. So because that force could change. And since it's force multiplied by distance, assuming that the things are parallel, then work done equals the area under the graph. Not needed really if you've got constant force, but as I say, if you have a force whose application changes, then that can be a useful relationship. So here's a question. So you're pushing an object, you push for 4 meters with a force of 10 newtons, and then over the next 4 meters, you're kind of getting a bit tired, so that goes down to 5 newtons. You keep that 5 newtons for another 4 meters, and then for 2 meters, you're saying, I've had enough of this, and you're stop pushing. Well, how much work have you done in total? Well, you can calculate that by looking at the area under the graph. Another situation is collisions. Now, we may have looked briefly at collisions before, and we'll look at them in more detail later, but a collision is where two objects collide or hit each other. So in this case, we'll have two balls of different potentially masses and two different velocities. And the ball on the left has a greater initial velocity than the ball on the right. So given time, it will catch up and collide. As it does, A pushes B. Now, a push, as we've seen, is an example of doing work. So if the orange ball is pushing on the blue ball, it's exerting a force, F2, and by Newton's third law, the blue ball is exerting a force on the orange ball, F1. What does A have that lets it do work on B? Well, A has energy. So work and energy, we think of them as the same thing, but another way of thinking of it is to say that the energy is the capacity to do work. You can only transfer energy by doing work if you already have energy to transfer. Energy can be defined as the ability to do work. So if A does work on B, then energy is transferred from A to B. And energy is also a conserved quantity, more or less. Under all situations that you would encounter on the physics syllabus and here on Earth, then energy is a conserved quantity, which means it cannot be created or destroyed. The amount of energy you have at the start of a process must be equal to the amount of energy you have at the end of a process. And energy comes in two different forms that we need to deal with. You may have learnt in previous years at school about many different forms of energy, and we can look at that, but in reality, they really are just two different forms of the same. No, every other type of energy is just really one of these two different forms. You have kinetic energy, which is energy due to the movement of an object, and you have potential energy, which is energy due to a position of an object. So, for example, the racing car has significant kinetic energy, and the spring or the apple as it falls has significant potential energy. There are many more examples. We'll look at some of these at least later. Here, for example, is an example of a tennis ball that has kinetic energy. Excuse me, how much kinetic energy does it have? Well, the ball has initial velocity, it hits, and it's squeezed. It's squeezed by the force on the ball, so it's exerting an acceleration. Forces cause acceleration, unbalanced forces. So the force is greater than the weight, at least initially, so it's an unbalanced force, it's accelerating upwards. And as it does so, it moves through a distance, S, displacement S. Work done equals force times displacement, negative in this direction because we're the force in the opposite direction, and force is also equal to mass times acceleration. So the work done equals negative MAS. This is a situation we'll assume of constant acceleration, v squared plus 2as. The final velocity is 0 because this is just as it comes to a stop, and acceleration is negative. Therefore, u squared equals 2as. The initial velocity is v, so v squared equals 2as. If we just redefine it to keep our definitions constant, which means that the work done equals, if as is half a v squared, v squared equals 2as, then as equals a half v squared, so the work done equals negative a half mv squared. Kinetic energy equals a half mv squared. Okay, so you didn't need to know that derivation, but it is a way of showing you that this movement energy, this kinetic energy, can be represented by the equation. We can determine this equation. We can derive this equation from the equations of constant acceleration, and from F equals ma, and definition of work, all to give us the kinetic energy equation of half mv squared. Okay, thank you very much.